All right, here we go into mean value theorem territory. And I start out with an awesome word problem that's actually not that bad. Everything in mean value theorem and a lot of things in calculus has to do with distance equals rate times time. I want you to keep that in mind as we go through this. The Cop Who Knew Calculus is what this is entitled. You were driving along the Garden State Parkway. It's a real highway in New Jersey, if you didn't know about that. It runs north and south, which has a speed limit of 65 miles per hour. You see brake lights ahead and figure there must be a cop. You slow down to be safe, and sure enough, there was a cop. 4 miles, so I'm going to underline that because there's some numbers there, 65 miles an hour, of course, too. 4 miles down the parkway, you notice more brake lights. Conclude there's another cop. Sure enough, you pass a cop just 3 minutes after seeing the first one. Thinking you beat the police at their speed trap, you continue on only to hear sirens and see the beacons turn as the cop you pass begins the process of pulling you over. Oh no. Following dialogue ensues. "Do you know why I pulled you over?" says the cop. "I'm sorry, officer, but it could not have been for speeding. I was going less than 65 miles per hour when I passed you back there." "Well, you were going as fast as you say when you passed me. I know you went 80 miles per hour at some point in the last 3 minutes. How could you possibly know that?" "I know calculus," says the cop. All right, I love this. It's corny, but it's hilarious. And it's a good example of the mean value theorem. So while you slow down at an instant to go 65 miles per hour by the cop, let's do distance equals rate times time to figure out your average velocity or average rate of speed in this case, because you're going in the same direction. If you had 3 minutes, that was your time. Now we're going to do this in hours because we have that we slowed down to 65 miles an hour, but 4 miles was a distance. We want miles per hour, not miles per minute. So 3 minutes, there's 23-minute intervals in an hour, so that would be 1/20th of an hour, or just do 60 divided by 3. And then the rate we don't have, that's what we want to find. But the distance that you drove, well, that was 4 miles down the parkway. So let's plug that in. We have 4 miles an hour, 4 miles that we went. The rate we don't know times the time, 1/20th of an hour. Well, to solve this, we'll divide both sides by 1/20th, right? It's the same as multiplying both sides by 20. So 20 by 4, if you multiply both sides by 20, will give you the rate. That was your average rate. So you averaged a speed of 80 miles an hour. This is why speed traps can work. So while they don't know how fast you were going at any one point in time to be sure, though, they knew that at some point you had to have gone 80 miles an hour. It's the only way you could average a speed of 80 miles an hour is if you went 80 miles an hour or more the entire time and then dropped back down to 65 when you passed them. There you go. So you could get a ticket for that. Point being is, what this is really saying, if you've got an interval where you have an average velocity of, in this case, 80 miles an hour, then on that interval, as long as the velocity, the position is measured with a differentiable function, which all things in this world are, you're going to guarantee that your instantaneous speed, you look down at your speedometer, had to have been 80 at some point. So that's all. That's pretty simple, right? So let's say you drive from your place on a bus to the local library, and you know that it takes the bus an average rate of 30 miles an hour. We don't ever look at the speedometer of the bus, but at some point on that trip, it had to have been going exactly 30. How many times it went 30 and when? We don't know. Just guarantees that it happens. So that's another kind of existence function, that speed had to have existed. It's in the family of intermediate value theorem as well. All right, so a real world definition. If you were in a car on a 2-hour trip and see that you traveled 100 miles, then there must have been some point in time such that the car was traveling at 50 miles an hour. Again, you traveled 100 miles for 2 hours, unknown rate. You solve by dividing by 2, and you'd have that the average rate was 50 miles per hour. So then at some point in time, your speedometer had to have been 50, even if you never looked down at it. Formally, here's the heavy stuff. Given a function, f of x is continuous on the closed interval, just like in Rolle's theorem, and differentiable on the open interval, meaning we're smooth from the starting point to the end point, then there exists some value c, some x value between a and b, such that the average rate of change, that's the slope, is equal to the slope at some instant at c. So let's go over this in a couple different ways to just round out this video, and I figured we'd keep it short. I'll go over the example, go over this in a couple different conceptual ways, and then in the next video, I'll go over a very typical problem on this. So you've got these two starting points, a comma f of a. This is the graph of f of x, this orange curve. b comma f of b is the other endpoint. It's smooth and continuous on that interval. And so what we see is we've got a slope of a secant line. Mean value theorem says there's got to be at least one point between A and B such that the slope of a tangent line is the same as the slope of that secant line. That's a geometric way of putting it. In other words, the average velocity, here you go, rise over run, is equal to the instantaneous velocity at some point. And last but not least, another way of looking at it, we've got the average rate of change is equal to the instantaneous rate of change at some point. So the slope of the tangent line at some point will be equal to the slope of the secant line on that interval. Bunch of different ways to look at it. Think of it as that cop problem though. Think of it as driving. If your average speed for a trip is however much, then you know that there's some point when your speed is a certain value. You know that for sure. That's it. I'll see you in the next video where we'll go over a defined type of problem that uses the mean value theorem. I'm psyched for it.